Okay, so picking up where we left off, boron is one of the exceptions to the octet rule. We know that we can expand the octet, but what about when we have an incomplete octet? Talked about hydrogen having the duet rule. Boron is just 3 bonds typically, so it only goes to 6. So just make sure you remember that when you see boron, it doesn't happen often, but when it does, just remember it typically is going to take an AX3 configuration, and that configuration is the trigonal planar. So everything is in a nice plane, 120 bond angle, 120-degree bond angle all the way around. So because there's no E, there's no lone pair, everything is symmetrical, right? 120 degrees, 120 degrees, 120 degrees. So even though fluorine is pulling the electrons and pulling the electrons and pulling the electrons away from boron, it's doing it in a symmetrical way. So overall, this will be nonpolar, right? If you have an AX, in this case 3, with no lone pairs, and all bonding elements are the same, it will be nonpolar. Now let's see what happens with SO2. It says it's angular or bent, not linear. So why would that be? Okay, so I'm going to start up here because I know I'm going to have to redo this and I'll show you. So we start with sulfur in the middle, oxygen on either side. When I go to count my electrons, sulfur's group 6, oxygen is group 6. So 6 times 3, I've got 18 total electrons to work with. Now I've used 4 electrons in those 2 bonds, so I have 14 electrons left. When I look, right, each of the oxygens would need 6 more to complete the octet, and the sulfur in the middle would need another 4. So 6, 4, and 6 is 16. Okay, so I know we've been kind of breezing through this because we haven't really needed any double bonds yet today. We talked about the scenario where if you have extra electrons, they go on the center element. But remember, this is the other problem. We don't have enough. I don't have enough here to just go and place the lone pairs. And what we talked about in the last chapter is, okay, that means I have to increase the sharing. 2 electrons short means I'm going to make 1 more bond. All right, so I'm going to make one of those a double bond. So oxygen on the left, I'll make that the double bond, single bond to the oxygen on the right. Then I'll put in my lone pairs to complete the octet. 2, 4, 6, 8 on the oxygen. Now with the single bond with 3 lone pairs. Oxygen with the double bond needed 2 more lone pairs, 2, 4, 6, 8. Sulfur needs 1 more lone pair to complete its octet. So when I look at this, my VSEPR is AX2E, but not quite. Let's think about formal charges. Okay, so if I look at my formal charges, the oxygen with the double bond, 1, 2, 3, 4, 5, and 6, right? This comes in with 6. We've assigned it 6, so that's 0. On the sulfur, it comes in with 6, but we've only assigned it 1, 2, 3, 4, 5. So 6 minus 5 means plus 1. Oxygen with the single bond, 1, 2, 3, 4, 5, 6, and then 7. So 6 minus 7 is a minus 1. And what we talked about was if you have a plus next to a minus, we can make that better if we can expand the octet on the center element. And the answer is we can. Sulfur can expand the octet. So based on formal charges, I'm going to take a lone pair from the terminal oxygen and move it to become a bonding pair. Now notice that does nothing to the VSEPR, which is good news because if we forget to do it, it won't hurt anything. So oxygen with the double bond, we're going to leave that as is. Sulfur in the middle is still going to have a lone pair, but now instead of single bonded to the oxygen on the right, it's going to have a double bond. And the oxygen on the right will now only have 2 lone pairs instead of 3. When I look at this geometry, all the formal charges are still 0. Now they're all 0. So this is a better structure because all my formal charges now have gone to 0. My VSEPR notation is still AX2E. All right. Remember, single, double, triple bond doesn't matter. They all count as 1X. So there are 2 bonding elements. So that's the 2. And there's just 1 lone pair on the sulfur. So that's the E, AX2E. So it's not going to be linear like the carbon dioxide was, where everything is in a nice, perfect straight line. Because now what's happening is there's another lone pair right up here, right? And that's going to bend the molecule. So now what happens is that sulfur center, because there's a lone pair here, it's bending the oxygens down. So that is an angular or bent molecule. So if I draw this or try to three-dimensionally, this one's not so bad. I'd have a sulfur center, lone pair, double bonded to the oxygen, double bonded to the oxygen. So now what's happened is because it's not in a straight line, this oxygen is pulling down and to the left. And this one's the right is turning down, pulling down and to the right, right? And there's nothing pulling up. So this is going to have a negative end and a positive end. But basically the rule is, like we talked about, when you have a lone pair, that takes away the symmetry, right? And when you don't have symmetry, it's very hard for it to be nonpolar. So this right here shows how it's going to be polar. We're pulling down and away from sulfur, nothing pulling up away from sulfur. So this is going to be a polar molecule because of that lone pair. So it's really important that you know how to do chapter 10 before you know how to do chapter 11. And then what's great is you really have to know chapter 11 before you can do chapter 12. Because what will happen in chapter 12 is it'll say, okay, well, why does boron trifluoride have such a low boiling point and silicon dioxide is higher? Like, or not silicon, sorry, sulfur. Why is that higher? And it comes down to what are called intermolecular forces. And that depends on if it's polar or nonpolar. So all of this sort of just goes all together. All right, so this one, polar, because of that lone pair on the sulfur. That takes away the symmetry. The more electronegative elements, which are on the end, are pulling away from the center element, but nothing pulling in the opposite direction. So that E, right? Anytime you got a lone pair, it's going to make it polar, with two exceptions, which I'll get to here in a little bit. BRCl, this one is pretty straightforward. And they're both halogens. They both just want one electron to finish out the octet. So they go into a single bond here. That's it. Polar or nonpolar, honestly, the electronegativity differences between these two is not very high, but we're going to just go with the simple definition, which is they are not the same element. One is more electronegative than the other. The chlorine is closer to fluorine, so that would create a negative side and a positive side. So we would say that that should be polar. All right. When we look at N2, we did this in the last chapter. Nitrogen ends up with a triple bond because both nitrogens want to pick up 3 electrons to complete the octet. However, those are both identical in electronegativity, so that is classic nonpolar. So the reason why I put these two in here was when we talked about polar and nonpolar, we were only looking at one bond, which made it really easy. It's a little bit harder to extrapolate that out to look at the entire molecule. But the idea is, and I think this makes sense, is that if the molecule is symmetrical, so it has an AXN, no E, if all those bonding elements are the same, the symmetry is there, so it will be nonpolar. However, if you throw in the lone pair, that takes away the symmetry from the molecular shape, and that's going to then make it a polar structure. Now, I had mentioned there are 2 exceptions, and you probably can guess which 2 they are. If I look at my VSEPR table, right, you see this one here, it's AX2E3. That would be linear because you've got a center element, whatever that is, right, bonded to 2 elements in a linear way, straight line. And then you'd have these 3 lone pairs on the center element. If I look at that, remember the more electronegative is on the end. So you'd have something pulling to the right, something equally pulling to the left. So as long as as the 2 X elements are the same, this possibly could be nonpolar. All right. And the other one here is, and I'll show you examples of this here in a little bit. This one here, the square planar, because what happens is you have your center element, you have an X up and to the right, and then equally down and to the left, up to the left and down and to the right. And it's in a plane, it's in the plane of the paper. You'd have a lone pair on the top of it, lone pair on the bottom of the center element. But the idea is it kind of makes sense because it's in the plane. That could also be nonpolar. Those are the 2 exceptions. So I'm going to write that over here, back where we were, right? It says AXN with no E will be nonpolar if all the bonding elements are the same. the two exceptions are AX2E3, which is linear, and the AX4E2 square planar. Makes sense because it's in a plane. These also are nonpolar, but again, only if all bonding elements are the same. All right. So again, always two exceptions. Always some exceptions. Those are the two for this particular topic. Okay, so the other thing we got to talk about is what's called orbital hybridization. And this is where I was really starting to say, I remember as a student being like, do we really know about these S&P orbitals? Is this really how this works? Because now you're telling me that all the rules are changing. So we learned about S, S orbitals being spherical shape. The P is along the axes. So we got the PX, PY, PZ. So then I remember when I was sitting learning VSEPR thinking, okay, I get covalent bond. You're telling me that the orbitals overlap because electrons are being shared. I get that. But how does an S orbital overlap with a PX, right? Or how does a PX and a PY overlap? Or right? Like I started to kind of just question, how does that work in space? Where these orbitals, which may not have the same shape, like an S versus a P, how do they overlap to where those electrons can be shared? And the answer is they don't. Okay, so what happens is the orbitals actually hybridize and you end up with the shape of the molecule. Now, how do they hybridize? And this is how it's gonna. This is where I was like, okay, I don't know if I trust this. So here's carbon. Now methane is CH4. CH4 has a carbon center, 4 bonding hydrogens, tetrahedral shape. Now, instead of drawing the shape, what I want to draw is the how this orbital hybridization happens. When I look at an energy diagram, all right, so carbon, we're just looking at valence electrons, right? Because that's where all the bonding takes place. Carbon has a 2s2 and it has a 2p2, right? That is as the atom of carbon. Okay, so when we were doing chapter 9, we would have said, okay, carbon has a helium core. The valence, there'd be 4 valence electrons because it's group 4, and the valence electrons would be 2s2, 2p2. Those are the outermost electrons. That was chapter 9. Now what we're saying is when carbon goes to bond, so this is now carbon that is bonding, the S and P orbitals hybridize. So instead of the P orbital staying up here in energy and the S staying here, they meet in the middle and they meet as one unit. All right. So we take that S and we move it here. And then we take those 3 Ps and we move it here. And instead of there being a double and 2 singles, we end up with 4 singles. All right. And what they call this is an sp3 hybridization. In other words, we need that S orbital and we need all 3 P orbitals to come up with 4 bonding sites. So what happens is you have your carbon with its 1, 2, 3, 4 bonds, right? Four electrons, I should say. The 4 valence electrons matching these right here. And then hydrogen comes in with 1 and another hydrogen and another hydrogen and another hydrogen. So what this is, this orbital hybridization creates the tetrahedral structure. So it doesn't stay S, PX, PY, PZ. It morphs into that tetrahedral shape, which is an sp3 shape. Right. And that's where that geometry comes in, which allows the hydrogen to bring in an electron and another hydrogen and another hydrogen, and another hydrogen. So we end up with 4 bonding sites here. So if we need 4 bonding sites, we need 4 orbital hybrids, right? We need 1, 2, 3, 4 spaces. So that's why we need 1, 2, 3, 4 spaces. All right. Now the S1, there is no S2, right? Because there is we're not looking at how many electrons anymore. We're looking at how many boxes. So the most we can have is P3 and the most we can have is an S1. So we just call it an sp3 hybrid. Now this part, I have to say, going through it, I was like, this is kind of confusing. But the good thing is that it matches your tetrahedral, right? Tetrahedral is always going to be sp3. All right, now when we were looking at the chart, right, we said that within the electron group of tetrahedral, you can have AX3E, which is trigonal pyramidal, and you can have AX2E2, which is angular, but there's still 4 electron groups. Now, tetrahedral is always going to have an sp3 hybrid. Okay, and I'm gonna give you a chart here at the end, which is going to be everything in this chapter in one place. So here's how these are all tetrahedral and all sp3. Okay, when I look at ammonia, the nitrogen center, ammonia, sorry, is NH3, right? If I look at nitrogen, it's an S2P3. So I'm going to do the electrons up here. So this would be the S2, 1, 2, 3, 1, 2, 3, right? There's my S2P3. That's just for the nitrogen by itself. When it goes to bond with the 3 hydrogens, it needs 3 bonding sites. Now, one of it does stay a lone pair, and then you have the PX, the PY, the PZ. But again, I need the orbital hybrid that will include, again, it's a hybrid, so they're going to equalize in energy, that will include the space for the lone pair and the 3 bonding sites. So you end up with 1, 2, 3, 4, sp3. You need the lone pair, and then you need the 3 bonding sites. So nitrogen, lone pair, hydrogen, 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 right? And we said it's trigonal pyramidal, right? Not planar, because that lone pair is pushing those hydrogens down. So this is trigonal pyramidal for the molecular shape, but the electron group geometry would still be the egg tetrahedral. So because it's tetrahedral, it's still sp3. So oxygen, what happens is when I look at its orbitals, it's an S2P4. So you have 2 pairs and 2 singles for the valence, those 6 valence electrons. When it goes to hybridize, again, we need all 4 of those. It's just 2 of them are going to have lone pairs, and then 2 of them are going to be bonding sites. So we still need the S and those 3 p orbitals. So when I look at water, H2O, oxygen in the center is going to have 2 lone pairs, hydrogen on either side. This is a bent, or sometimes called angular molecular shape, but the total number of electron groups for all 3 molecules here stays exactly the same. So if I just look at them in comparison, right? Here's my CH4, right? 1, 2, 3, 4 bonding elements. I need 4 bonding sites. I need 4 orbital hybrids. So I need to take the S and 3 P's. So there's my 1 plus 3. There's my 4 orbital hybrids. Tetrahedral, right, means there's 4 electron groups. 4 electron groups means I need 4 orbitals, right? So it doesn't matter if they're lone pair electron groups or if they're bonding pair electron groups. If I need 4 groups, I have to have 4 orbitals. Now with nitrogen, with ammonia, one of those hydrogens is now a lone pair, right? So now I've got a lone pair, 3 bonding hydrogens, but I still need a spot for the lone pair, and I need a spot for the bonding site, bonding site, bonding site. So lone pair on the nitrogen, 3 bonding sites. I still have 4 orbital spaces needed. It still comes under the 1, 2, 3, 4 electron group geometry of tetrahedral. Now the shape, what I actually see, just the nitrogen and the 3 hydrogens, is trigonal pyramidal, but it still has 4 total electron groups around it, which is why it's still an sp3. If I do this one more time, and now that black molecule instead of nitrogen is an oxygen, right? So here's my oxygen with my 2 lone pairs. Here's my 2 hydrogens bonded. What I see, just the black ball and the 2 white balls, I see a bent molecule. but I still need 1, 2, 3, 4 total electron groups. So I still need 1, 2, 3, 4 total orbitals. 2 of them are lone pairs, 2 of them are bonding sites. So it's still an sp3 hybrid. So whenever you have an electron group geometry of tetrahedral, it will be an sp3 orbital hybrid. That makes it very simple. So when you get your chart for the test, you're going to remember when there's 4 groups, right? You need 4 orbitals. 1, 2, 3, 4. 1 plus 3 is 4. It will be an sp3 hybrid. Okay. Now, what if it's only AX3? Now I only need 3 spaces. That means it would only be an sp2 because now I just need the 1s and the 2 p's. And if it's linear and there's only 2, then I only need 1 plus 2. So I only need sp hybrid. All right. When does that happen? All right. So if I keep going, trigonal planar. Okay. So trigonal planar is when you have your AX3, right? All of these are in the AX4 family. When you have AX3 trigonal planar, only 3 bonding sites needed. We just need sp2. And the molecule we saw for that was boron trihydride. So here's what happens. When you look at boron by itself, it's an S2 P1, all right? When it goes to bond, it only needs 3 orbital spots. So you take the S and then you take 2 of the P's, and then you might be like, well, where's the other P orbital? Okay, so I'm going to draw it like this. That other P orbital is still just up here hanging out empty by itself, not used. We only need 1, right? These 2 electrons, they split apart, and then this one goes here. So there's my 1, 2, 3 bonding sites, extra P orbital just left over for who knows what. So that's why this is just an sp2 orbital hybrid. All right, and the boron trihydride, like we saw before, it is, well, we saw boron trifluoride, but it's the same idea. It's 120-degree bond angle, AX3 symmetrical. Carbon dioxide. All right, here's where it gets a little bit trickier. Carbon, we had said, all right, carbon starts out with an S2, P2. And then when we said when it goes to bond, right, it does usually the tetrahedral, but this one's different. The reason why this one's different is because the carbon dioxide, instead of single bonds, it has double bonds. Okay, so then you're like, well, now what happens? Okay, so this is the carbon atom by itself. Now let's look at the carbon in the CO2. So what happens now is I need 2 bonding sites. So I'm going to take these 2, right? This one and this one. I'm going to put these at a kind of a lower energy level. And then these 2 are going to stay up here. All right, now let me see if I can color code these. So here's this one moving over, moving a little bit higher up in energy because it's hybridizing, partnering with this one up here, moving down in energy because it's hybridizing. And the 2 that aren't hybridizing, they're just going to kind of stay right at their same energy level. All right, that part you really don't have to worry about, but this is what happens. Because these are double bonds, the first part of that double bond is called a sigma bond, right? That's like the baseline. But there's a second bond here, and that's called a pi bond. So the double bond is the pi bond. The single bond, or the first part, is called the sigma bond. So I just remembered sigma for single. That made sense. A pi bond adds to a sigma bond. So you have to have a sigma bond first, right? So like this right here is your sigma bond, and then we add to that a pi bond. But we had to do that again over here. So we have another sigma bond and then another pi bond. So that's where those 4 electrons go for carbon. We still have 1, 2, 3, 4, 1, 2, 3, 4 valence electrons. It's just what happened now is I have a double bond, and then I have another double bond, right? And what they do is they overlap. And if you remember, that's exactly what this looks like, right? So here's your carbon center. Here's like what you could kind of connect it here. Here's your sigma bond. There's your pi bond. That makes a double bond. All right. And then the other one sigma bond, pi bond, that makes your double bond. So carbon with the 4 valence electrons, right? 2 of them are going into that double bond on the right, and then the other 2 are going to the double bond in the left. And the pi bond always is at higher energy than the sigma bond. The sigma is always like the baseline. So this is a stack, right? And if you had a triple bond, you would have a sigma and then 2 pi bonds, right? Because there would be double, I can't say double to make a triple, be a sigma and then 2 pi bonds to make a triple bond. But this right here is why when we look at the orbital hybrid, it's only an SP because we're always looking at the sigma, like the baseline, what's the orbital hybrid? So what you need to connect, what's the easiest way to do that is if it is AX2, that means I only need 2 bonding sites. And remember for Vesper, it doesn't matter if it's a single bond, double bond, triple bond. So I only need 2 bonding sites. So that means I only need 2 orbital spaces. So I need an S and only 1 P. The other 2 P's are going to be up here in the pi bond space. Okay, so just what I need you to make sure to connect is 2 bonding sites, I need 2 orbitals. If I've got 3 bonding sites, I need 3 orbitals, right? If I have 4 bonding sites, I need 4 orbitals. If I have 3 bonding sites in a lone pair, that's still a total of 4, so I need 4. If I have 2 and 2, that's a total of 4, so I still need 4. All right, so that's the idea with this orbital hybridization. So if you have, and this will go back to where I was saying, I was going to try to get all of this on a chart for you. All right, and this, what I'll do is I'll scan this on Thursday and post it in case it's helpful, but it might be just a nice way to review some of this because there's a lot of information here. No, there's obviously that's an obvious, and I still have more to talk about. But the AX2, right, the linear, if this is test A, this is kind of what the chart would say. It'd say AX2, this is blank. Right? We don't know what that shape is, but I think that one's probably really easy to remember, right? You would say AX2, that's going to be linear. So I highlighted that because you need to remember that that's linear. What I also need you to remember is what would be that orbital hybrid. And again, the idea is if I only need 2, I'm going to always start S is the lowest, right? So I'm going to take an S and 1 P, right? There's my 2 orbital hybrids. If I have AX3, I need you to remember that AX3, that's when you have the symmetry. That would be the trigonal planar, right? Example there was the BF3 or the BH3. Now with 3 bonding sites, I need 3 orbitals. So again, I take S as the first one, and then I would need 2 P's. All right, now if I have AX2E, which is bent, which was that SO2 molecule we saw earlier, right? 2 bonding sites and a lone pair up here. So all we see is bent, but the egg, right? The electron group geometry is still trigonal planar. There's still a total of 3 orbitals we need. We have 2 bonding sites plus a lone pair. Now, granted, these are double bonds, but again, doesn't matter. You've got 2 plus 1, so a total of 3. It's going to be sp2. All right, so remember how we were tying the electron group geometry? There are 5 main electron group geometries. It turns out there are 5 main electron group geometries and there are 5 orbital hybrids because they're connected together. So if I went and tried to summarize your table, right? If we go back to the table here really quick, if you only need 2, right? 1, 2, SP. If you need 3, 1, 2, 3, sp2. If you need 4, whether it's lone pair or bonding pair, it doesn't matter. Total of 4 electron groups, tetrahedral. You need 1 plus 3 is 4. If you have 5, this is where we're going to expand the octet because now we're going to tap into the D. So now we've got 1, 2, 3, 4, 5 total groups. So we had to bring in the D. Orbital hybrid, when you have 6, would be sp3d2, right? Because now, again, we had to expand the octet. All right, so the diagrams that I was drawing with regard to the electrons and how they hybridize, really, I need you to just be able to know that if you have 4, it's sp3. I don't need you to know if I go back to where I was in the notes. Sorry, just 1 second. I got papers everywhere. I don't need you to remember exactly how they hybridize and overlap and what did I do with that sheet of paper? Ah, there it is. I don't need you to be able to draw this. Like hybridizing the S&P, to me, once I learned that, it did help me understand it, but you don't really have to do that. All I need you to be able to connect is if I need 4 bonding sites, I need 4 orbital hybrids. If I have a lone pair and 3 bonding sites, then I need you to still have 1, 2, 3, 4 orbital hybrids, right? So still sp3. So it turns out your orbital hybrid is directly linked to the electron group geometry. So remember when we were talking about the electron group geometry, there's only 5. So if you know it's linear, you know it's SP. If it is trigonal planar, AX3, then it's SP2. If it's tetrahedral, SP3. Once you've expanded the octet, we've now tapped into D because remember, there's only 3 p orbitals, so we can't do any more than that. So at this point for AX5, we'd have SP3 with 1 D. So 1, 2, 3, 4, 5 spaces. Octahedral would be SP3D2. Now there's a total of 6, right? 1 plus 3 plus 2 is 6. All right. So I'm going to like complete this table and finish it and post it on Thursday, but I want to make sure and continue on with the notes so that I don't lose some of our time. So where we left off, right? We were looking at trigonal planar, AX2. Now we hadn't gotten to expanded octet. So now let's look at expanded octet. Okay, so for phosphorus, we had mentioned if we look at phosphorus just by itself as the atom, right? It has a 3s2, 3p3. Okay. So what's different is nitrogen, right? When it hybridized, it went with only 4 orbitals and it did lone pair and 3 bonding sites, and that was it. But phosphorus can expand the octet. So instead of doing a double, single, 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 is it can bring in the d orbitals that are also there. It'll just bring in one of those to create 1, 2, 3, 4, 5 bonding sites. Now, 4 of those d orbitals, those would still be up here, right? They haven't moved. They're just still hanging out. Okay. But that's why with phosphorus, you can get an expanded octet as we can tap into the d spaces. All right. So when you have AX5, it's going to do that thing again where it freezes. Let's see if I can do that. Oh, okay, that's good. When you have AX5, you need 5 orbitals, right? So 1 plus 3 plus 1, sp3d. If you have octahedral, there's going to be a total of 6, right? sp3d2. All right, we won't worry about that. Now, octahedral, what does it look like? Because I haven't showed you that yet. Sulfur hexachloride, we would have sulfur in the center. You have a chlorine on top, chlorine on the bottom, chlorine going to the back, chlorine coming out to the front, chlorine out to the front, chlorine to the back. All right, so this is your octahedral, right? So you'd have your sulfur center, top and bottom, chlorine, chlorine, down and away, up and away to the right, down and back to the left, up and out to the left. So that's your octahedral shape. Again, why octa? Why did they say octa? Why wouldn't they do hexa? Don't understand, because in nomenclature, hexa means 6, right? Sulfur, we didn't say octachloride, we said hexachloride. So why is the shape octahedral? I don't know. I never found a reasoning for that. All right, octahedral is what it is. Okay, so let's look at another example. All right, let's talk about silicon tetrachloride. Talk about the Lewis structure. This is going to kind of review a little bit of everything. Now, I know we already did silicon tetrachloride. So we've got silicon in the middle, got chlorine on top with 3 lone pairs. We got chlorine down and to the left, 3 lone pairs. Chlorine down and to the right, out of the paper, 3 lone pairs, down and to the right, in the back of the paper, 3 lone pairs. All right, AX4, which we know is tetrahedral. That one's easy to remember and logical. Tetra we know means 4. If I look at all my formal charges, okay, all formal charges here are 0, which is what we want. If we don't have a polyatomic ion, 0 is best. Okay, all formal charges are 0. We didn't expand the octet here. Didn't need to, right? Silicon could, but didn't need it. Is it polar? Okay, so we said that if there's no lone pair, this symmetry is there. All terminal elements are the same. So this would be nonpolar overall. All right, so nonpolar molecule. Then the orbital hybrid, because I need 4 bonding sites, I would have an S and 3p for the orbital hybrid. All right, sp3 orbital hybrid. Now, the electron group geometry, right? 4 total groups, tetrahedral. And what I was trying to say earlier, but I know there's a lot of information thrown at you, is when you don't have an E, no lone pair, the molecular shape or molecular geometry is the exact same as the electron group geometry. So in this case, both answers would be tetrahedral. All right. It's only when you have a lone pair that the electron group geometry and the molecular geometry are no longer the same. Okay, so that would be silicon tetrachloride. I'm going to do another one of these in just a minute on the back of this page. When I was learning orbital hybrid, the professor only did carbon-based molecules. And then I was trying to tie it together with, okay, if it's a single bond on carbon, it's always sp3. If it's a double bond, it's sp2. And that is not a great way to do it. But I was just trying to pattern it, like put everything into a pattern. Now I understand this so much better. It's linked to the geometry. Ethene, if you're like, I don't know what ethene is, don't worry. C2H4, I would tell you it's C2H4. So in this one, we have a double carbon center, and then we'd have 2 hydrogens on each side. Remember, symmetry is always your guide. But carbon, we know, likes to have 4 bonds. So there's a double bond there. Now, if you went through the Lewis structure, I think we did this maybe last week, but you would have not enough electrons to complete the octet. So you end up with a double bond there. Now, what happens here with Vesper? Because you technically have 2 centers, right? You're looking at this center carbon. Let me cover up these 2 hydrogens over here, right? This is one of my centers. If I look here, that carbon has an AX3, right? There are 1, 2, 3 bonding elements, and there's no E. If I look at the other carbon center, guess what? It has the same, because it's symmetrical, makes sense. It's also AX1, 2, 3. So AX3. So AX3 for both carbon centers. All right. So that means that both of those carbons, right, would have a trigonal planar geometry. Now that would be the electron group geometry and the molecular geometry, because there's no lone pair, right, on the carbon. So they're both going to be the same. Orbital hybrid. Well, if it's a 3, we only need 3, right? So that means S and 2 Ps would be the orbital hybrid. It's for both carbons. So when you have a molecule that has 2 centers, you're really doing this twice, but if it's symmetrical, it's the same for both, right? So both of them are AX3. So both of them are trigonal planar. So both of them are sp2 hybrid, right? So when I was a student and I was trying to piece this together as best as I could, because I just didn't get it taught to me this way, I remember thinking, okay, if carbon has a double bond, it's going to be sp2. But that's not always the simplification you want to use, because like in the case of carbon dioxide, there were 2 double bonds and that made it only sp. So what I want to show you here really is the sp2 is because it is an AX3 notation. That's what will never steer you wrong. If you know the Vesper, you know the orbital hybrid. Acetylene is C2H2. And so now what happens is you have the carbon triple bonded to the other carbon. So again, it's a 2 carbon center. So if I look at the carbon on the left, it is AX2, right? There's my carbon center, 2 bonding sites, so X2. When I look at the other carbon, symmetrical, looks exactly the same. There's my X2, no E, right? We said AX2 is linear. And because there are two bonding sites, we need an sp hybrid, right? Sp, because there's only two orbital spots needed. All right, so the sp is because it is an AX2, right? And that was like the case of CO2. That was the other example. That was AX2. All right, and that also was an sp hybrid. So it's not just that it's a triple bond. It just depends. Really, it goes back to the geometry. So if carbon only has two bonding elements, it's going to be sp. If it's got three bonding elements, it'll be sp2. But it really goes back to your VSEPR. If you know the VSEPR, you know the orbital hybrid. So now what I'm going to do is go back to that chart. Okay, so I think we might be able to get this done before we're done today. So as we were just looking at, right, the acetylene, the CO2, those are both examples of the carbon center having an AX2 linear geometry. And that means linear because we only have two bonding sites is going to be sp. Now you do need to know sigma and pi. Now in the case of carbon dioxide, you would have two sigma bonds and two pi bonds. All right, because they're two double bonds. So here's a sigma and a pi and a pi. With the acetylene, the carbon hydrogen bond, right? That's just a sigma. A single bond is, just remember, sigma is single. When you have a triple bond, okay, the triple bond means you have a sigma and two pi bonds, right? That's how you get a total of 3. So this is like your sigma, pi, pi, right? You overlap, right? And the book does a really good job of illustrating what those look like, but it's, to me, it kind of just matches what you draw, right? So your sigma is always the base. And then you have anything overlap, like on top of that would be a pi and a pi. So a sigma, pi, pi makes for a triple bond. If it's a double bond, it's just a sigma and a pi, sigma and a pi. Now, AX2 is what you need to remember. It means it's linear. And then because there's only two bonding sites, you need to remember that's sp hybrid, right? If it's AX3, you need to remember that's trigonal planar. That's why I highlighted it. Example was boron trifluoride. That means I need 3 orbitals, right? So 1, 2, 3, sp2. If it's AX2E, doesn't matter that I've got a sigma and a pi and a sigma and a pi, because what would happen here is for sulfur, you would have this baseline with the lone pair and a electron, and then on top of that, you would have your pi bond. So remember how sulfur has 6 valence electrons? They're still here. 1, 2, 3, 4, 5, 6. Just 2 of them are going into that double bond. 2 of them are going into another double bond, and then 2 of them are in the lone pair. So that's what that hybridization would look like. But when we look at the orbital hybrid, we just look at the baseline, and that baseline is sp2, all right? But you don't really need to know all this. You just need to know I need 3 total spaces, 2 bonding sites and a lone pair. So 1, 2, 3, 1, 2, 3, okay? When you have anything in the electron group geometry of AX4, you're going to want to remember that that's tetrahedral, right? Tetra makes sense for 4. And if it's tetrahedral, now we need 4 bonding sites. So sp3, right? So it's got 1 plus 3, so 4 total. Now, within that, if I swap one of those bonding sites for a lone pair like we did with ammonia, there's still 1, 2, 3, 4 total electron groups. So it's still tetrahedral for the electron group. The shape is trigonal pyramidal, but the orbital hybridization is the same, still sp3. When we took off another one of the bonds and turned it into a lone pair for water, 2 lone pairs, 2 bonding pairs, I still have a total of 4. 1, 2, 3, 4. So the electron groups, 4, still tetrahedral, but the shape, what I see is a bent molecule. 4 sites, still sp3 hybrid, right? So notice when I'm in anything of a total of 4, 4 plus 0, 3 plus 1, 2 plus 2, all sp3, all right? Now after that, we have to expand the octet. When you get to AX5, right, this was the one I showed you. This is the 2 pyramids. So trigonal bipyramidal. All right, and if I have a total of 5, this is where I've expanded the octet. I have an sp3d. 1, 2, 3, 4, 5, right? Antimony pentachloride was one of these. I need 5 bonding sites, so I need 5 orbital hybrids. If I have AX4E, 4 plus 1, still 5, still 5 orbital hybrid. This one's called seesaw, but that'll, remember, if it's not highlighted, that's going to be on what's given to you. So it'll say it's seesaw. AX3E2, T-shaped. We saw the chlorine trifluoride. 3 plus 2, still 5, still need 5 orbital hybrids. The AX2E3 linear, still total of 5, right? So seesaw, T-shaped, linear, AX2E3 linear, not to be confused with just AX2 linear, but all of these here have the same electron group of trigonal bipyramidal. The shape is different. What we see is different because now we got lone pairs that we don't see. But what we see are the bonding pairs, right? All the bonds and the molecule structure we see. So what's here is the molecular shape. I need you to know the electron group, right? So that will be there. If there's no E, the electron group, molecular shape, same thing. The orbital hybrid, same for all of these. We have a total of 5, whether they are bonding sites or lone pairs. They are all a total of 5 sp3d for the orbital hybrid for all of those. So the orbital hybrid, I remember really kind of racking my brain on that and then realizing it's so simple. It's just connected to the number of electron groups around the center element. So if you have 5 total electron groups around the center element, you need 5 total orbital spaces, right? If you only need 4, you only need 4. So I wish my teacher had taught it to me that way. Would have been so much easier. Okay, then the last one here we got to do is, and again, I'll put this, I'll scan this and post this on Thursday, is when you have AX6, right? So sorry, I had the marker cap in my mouth. So AX6, I need you to remember that electron group, that molecular shape, when it's AX6 is called octahedral. The example they had there was SCl6. I showed you what that one looked like. That was this one here, right? That's the octahedral. AX6, 6 bonding sites, 6 orbitals, sp3d2. That's where we max out. We don't have anything past that. All right, if we have AX5E, okay, we've lost one of these. All right, so now one of those is now just a lone pair. This makes sense. If you kind of think about it, maybe this way would be easier. This is a pyramid, but the bottom of it, instead of a triangle, is a square. So it makes sense, although this would be given to you, it makes sense that that's why it's called square pyramidal. All right, and again, 5 plus 1, it's still sp3d2, total of 6 spots. When I get to AX4E2, this is the one that's called square planar. All right, when it's square planar, what we see, right, is this perfect square. We don't see the lone pairs. The molecular shape is just square planar. So there's my square. It's in the plane of the paper. So here it makes sense. This can be one of those, this is one of the 2 that's nonpolar, right? If I'm pulling up and to the right and down to the left at exactly that 180-degree bond angle, nonpolar. Same in the opposite direction. So this is the one where it's possible that it has a lone pair, but it still be nonpolar, and that's because it's planar. All right, still sp3d2. All right. So when you get your chart for the test, what I need you to remember, right, is what I have in highlighted here will not be given to you. So you're going to need to know those main electron group geometries. I'm also going to need you to know the orbital hybrid that goes with that electron group geometry. And then I need you to also know, when is it polar? When is it nonpolar? This is going to be a big thing when we get to chapter 12 on Thursday. If you have a lone pair, it will pretty much always make it polar, except when you have linear or square planar. In that case, in all other cases, right, if you have an AX, no E, and all terminal elements are the same, it will be symmetrical, it will be nonpolar. So that can happen if you have linear or square planar, again, as long as the terminal elements are the same. So there's a lot of information here, right? This right here, what I have highlighted, I don't know how much it helps, but it might. I'll scan that and bring that. I'll scan it on Thursday and post it. But that finishes chapter 11. I know it's a lot. I know one of the questions was, again, do you need to know this? And the answer is no. I just need you to know that if you have a total of 4 electron groups around the center element, you're going to have a 4 orbital hybrid. So 1s and 3 p's. If the electron group geometry is tetrahedral, it's going to be an sp3 hybrid. If it's trigonal planar and I only need 3, then it's going to be sp2. So I think that's easier. I don't think you have to know this, but I was always a person to ask why. Why is that the way it is? I still do that. So that's why I like knowing this. But if you don't want to know that, don't worry about it. I just need you to tie the electron group geometry to the orbital hybrid. The sigma versus the pi, that I also need you to know. Just remember, sigma means single. A pi is in addition to a sigma. So a double bond is a sigma and a pi together. A triple bond is a sigma and 2 pi's together, right? So that's what I need you to know about sigma and pi bonds. Other than that, I think that's everything. Sorry for going a little bit over. If you have any questions for me, let me know. But otherwise, I'll see you back here on Thursday.